Hello, in these sessions, we will talk about the concept of a nuclear reactor, which include a reactor, a turbine, a condenser, and a generator. So in the world, there are many nuclear reactors installed in different countries, and most of them are installed along the coastal area where plenty of waters are available for the cooling. And there are many different types of nuclear reactor. Some using water to cool down the reactor, some using gas or even liquid metal. But in this course, what you need to learn is those nuclear reactor using water cooling. Amongst the water cooled reactor, some use light water moderate, some use heavy water, some even use graphite. And the differences between light water and heavy water is that light water is our ordinary water, the normal water, H2O. H has one proton, while heavy water is also H2O, but this is the isotopes of hydrogen with one proton and one neutron. So the molar mass is double and therefore is heavier. And there are two types of light water moderate reactor. One is called the boiling water reactor and another is called the pressurized water reactor. In most of the installations in the world, we use nowadays the pressurized water reactor, which is more than half, and then the next is the boiling water reactor. For the rest are those other different types of reactor that are not so important, and because the technology is maybe either too new or too old. In this nuclear reactor, there are two processes to control the temperature inside the reactor. One is by controlling the cooling effect, the amount of heat to be taken out from the reactor. And we take away the reactor temperatures so that we can keep it in a safe temperature range. Another method is to make use of a process called moderations. We control the rate of nuclear fission reaction. Another process is called moderations. So we control the rate of nuclear fission reactions inside the reactor. So we add some control rod, which is made up of graphite, to slow down the process of the neutron hitting on another uranium. When this control rod fall down into the reactor core, then the neutron emitted from a nuclear fission process could be stopped by the graphite. This diagram shows the typical structure of a boiling water reactor. The reactor with the nuclear fuel will generate heat to heat up the water inside the reactor and turn into steam. And this hot steam at around 280 degrees Celsius will then pass to a turbine and move the turbine. And then this energy conversions from heat energies to kinetic energies and then to electrical energies can generate as electric energies in the power plant. After this kinetic energy conversions, then the water vapor will be condensed and cooled down and turned back into liquid form, and this liquid water will go back to the reactor to heat up and then repeat the process again. Therefore, in a nuclear reactor, we need plenty of water to cool down the hot steam so that it can continue this cycle. So in the boiling water reactor, water is passed to the reactor and turned into steam. And there are some physical contact between the water and the nuclear fuel. And the water vapor, the steam, will be radiated. We have some level of radiations, and it will be dangerous to the public if there's any leakage in the turbine. On the other hand, in the pressurized water reactor, there are two loops. One loop is confined within the containment structure. So water inside the reactor will be heated to a much higher degree, 325 degrees. The water in this primary loop is under high pressures, and although the temperature is 325 degrees, it can still be maintained in a liquid form and circulate in this primary loop. There's a secondary loop here that take up the heat from the primary loop and heat up the water and turn into steam, and the steam will then move the turbine. The temperature of the steam in the secondary loop is about 280 degrees Celsius, and then after passing through the turbine, it will be condensed and turned back into water and then feed into this secondary loop to pick up the heat energies from the primary loop again. So this is the second circle. So by doing so, the dirty water, which have been in direct contact with the nuclear fuel, will not be lead to the environment, because the temperature exchange, heat exchange between the primary and secondary loop occur inside the containment structure will be quite safe. Even though there are leakage outside the containment structure, those dirty water which have been radiated by the reactor will not be leaked to the public. The key point in pressurized water reactor is that there's a secondary circuit that can take away the temperature from the primary circuit, and this occurs within the reactor building, which is much safer. This diagram shows the differences between the boiling water reactor and a pressurized water reactor. So basically, for the pressurized water reactor, there is a secondary circuit, and the heat exchange occurs within the reactor building. For the boiling water reactor, there's only one loop, and the heat exchange will be directly occur inside the reactor. And in the boiling water reactor, there's only one loop, and the heat exchange will be inside the reactor vessel, and the polluted water will pass to the turbine directly. Therefore, in general, the pressurized water reactor is safer than the boiling water reactor, and most of the recent installations are using pressurized water reactor. In March 11, 2011, there was a tsunami in Japan, and which as a result triggered a serious nuclear accident in a place called Fukushima. So this accident reminds us that nuclear energy is good, but at the same time, it may be risky if we cannot do enough safety measures. There are some international guidelines that govern the operators what are the reasonable amount of dosage that those workers working in a nuclear reactor can expose. For example, a worker can expose to 20 million Celsius in average for 5 years. And for general public, it's just only 1 million Celsius for an average of 5 years. So what's meant by Celsius? Celsius is an SI unit that measures the ionization of the radiations. It is used to measure the external radiations of the source outside our body, or if you have eaten or inhaled any substance with radiations, that this internal radiation inside your body could also be measured. So the definition is 1 Celsius is equals to 1 joule of energy divided by a kilogram of your body mass. For example, when you take a flight from Tokyo to New York, you are receiving 0.19 millisieverts. And when you do a CT scan, the radiation is about 6.9 millisieverts. And compared with the radiation level in a nuclear power plant, the target radiation is only 0.05 millisieverts. So in other words, it's more dangerous for you to take an airplane than exposing to the radiations in a nuclear reactor. But if the exposures of radiations is too much, let's say over 1000 millisieverts, so which is almost more than 100 times for CT scan, then it may cause you cancer. And if the exposure level is 10,000 millisieverts, it may cause serious radiation sickness. And if it is more than 10,000 millisieverts, it will kill you. According to the International Nuclear and Radiological Event Scale, there are 7 scales starting from 0. The first 4 scales from 0 to 3 is what they call an incident, and from level 4 to 7 is an accident. For instance, it means that there are some operational issues and some incident or serious incidents happen in the nuclear power plant, and they just need to take a record. But for level 4 to 7, these are considered as accidents. For those accidents that occur inside the reactor may cause some local consequence, so only those people, the engineers working in the reactor, may be affected. But there are some wider consequences, let's say a leakage in the pipe, so that the radiated steam may then expose to the atmosphere, and the people surrounding those areas have to be evacuated. And there are some serious or major accidents that maybe the whole city, like Fukushima, has to be evacuated. So there are 3 major nuclear plant accidents happened in the man history. So in 1979 is the Female Islands nuclear reactors accidents. 1986 is the Chernobyl accidents in Russia, and then year 2011 is the Japan Fukushima nuclear reactor accidents. So what are those levels? Can you make a guess? So in the Female Islands is level 5, and then for the other 2, Chernobyl and Fukushima, they are both level 7, which means that major accident, very serious. And engineers learn lessons from all these accidents. So for the Female Islands, it's due to the misoperations because of the man-machine interface designs is not that clear, and it mislead the operators. And after that, there have some improvement in the ergonomics and instrumental displays, and help those engineers and operators operate the system in a more effective and safety way. In the Chernobyl accidents, there was some fundamental power plants design problem, and afterwards they revised the design and commit to safety culture, and also exchange the best practice with other nuclear reactor operators. And then for the recent Fukushima accidents, this accident is a result of a multiple event. And first, they have an earthquake, and then it triggered a tsunami, and the tsunami triggered a huge water wave that flooded the cooling plant. And when the cooling plant is out of service, then the temperature built inside the reactor will keep on increasing and finally burn the reactor. So after human beings experience all this pain, and we learn lessons from these accidents, so we can now improve the designs of a nuclear reactor with different generations, and from generation 1, 2, 3, and now evolving to the 4th generations. As we discussed earlier, we improve from just one single loop to 2 loops. So this is one of the measurements on safety to safeguard the polluted water will not be leaked to the surrounding. And we need to take away the heat from the fuel by an effective cooling system. But then, what if the pump of the cooling system is malfunctions? And this happened in the Fukushima nuclear accidents, when the water pump was flooded by the seawater and stopped functioning. No cooling, temperature increased inside the nuclear reactor and finally burnt. So we learn lessons from these accidents, and we improve our engine designs from an active engine system to a passive safe features. So it means that in the past, we need to actively supply an energy to the water pump to maintain the circulations. And this is not very reliable, because When the power supply to the water pump is stopped, then no power supply, the pump is not working, and the cooling system will then malfunction. So now we prefer a passive safety features, which means that the system could passively operate by itself even though there is no power supply. It can be done by the remaining pressure, using the remaining pressure of the steam to power up, to move the water pump, so that even though there's no electricity power supplies to the water pump, the remaining pressures can still move the pump and continue the cooling process for a while. Apart from the cooling system, we also use a method called moderations to control the rate of reactions inside the reactor. And we use control rock, the graphite rock, and also boric acid. The boric acid could help to absorb some of the neutron and avoid them from hitting with other uranium and continue the chain reactions. For the control rod will be lower to the nuclear fuel and stop the neutron from hitting another uranium. How should we design the reactor in such a way that the control rod can be effectively moved down to the nuclear reactor while there is an accident? What is the most reliable force in the world? Should we use a motor to rotate some gears and then move down the control rod? Or what can we do? What is the most reliable force in the world? Gravity. Okay? When we release a cam, then this control rod can drop to the reactor, and this is the most reliable. And we can make use of a electromagnet to hold the control rod and apply a current to hold it, and when emergency, this current will be terminated. Okay, the circuit will be open, or the power supply to hold this rod will stop. Then the control rod can be released and dropped to the reactor. This diagram summarizes the safety measures of a pressurized water reactor. First, there are two circuits. The primary circuit takes the heat from the reactor to the secondary circuit, and even though the secondary circuit has some leakage and the steam inside the secondary circuit is exposed to the atmosphere, doesn't matter because those water is still clean. It does not have any direct contact with the nuclear fuel. And the second safety measure is that during the shutdown and even the complete power loss, steam is used to drive the feed water pump and continue the cooling process. Compared with the boiling water reactor, when there's only one primary loop, so when there's a leakage in the steam pipe, those dirty water will have direct contact with the nuclear fuel, will then be exposed to the atmosphere, and then people surrounding this area has to be evacuated. On the other hand, in the radio reactors, there is a containment building which contain and protect all the major equipments and facilities inside this reactor. So, the safety measures including there's a fuel catering that used to protect the nuclear fuel, and there is a reactor pressure vessel, and the thickness is about 200 millimeters that protect the core. And in the whole compartment building, in the whole containment building, there is a 900 millimeters thick concrete that with 6 millimeters thick. And for the whole containment building, the thickness of the concrete wall is about 900 millimeters. And inside this concrete wall, there are 6 millimeter thick steel lining that protect the overall structures. So even a jumbo 747 aeroplane crash on the nuclear reactor, the nuclear reactor will still be okay. Only the airplane will be crashed. In the future, there are many new technologies that are being developed and researched to improve the safety and efficiencies of a nuclear reactor. For example, some engineers are designing how to make use of high temperature gas cooled temperature design, and so that the temperature can be much higher and the heat transfer efficiencies can be improved. And some may use what they call the fast neutron reactor and make use of liquid metal sodium as the coolant instead of using water, and some nuclear reactor may also use plutonium as the nuclear fuel. So there are many different ongoing development and improvement, and hopefully mankind can develop a much safer and more effective and clean energy using nuclear power in the future.